So good afternoon, everybody. I would first like to welcome each of you to our Loenbro webinar training series. Our goal of this series is to be an informative resource to not only our employees and business partners, but also our clients in regard to key industry topics. For those of you that I haven't had the fortune of meeting yet, my name is Parrish Furr, and I will be your host for today. I'm the Principal Level 3 and the Director of Quality for Loenbro Inspection. I'm also joined by Ms. Sabrina Coleman, who's Loenbro Inspection Superintendent of our Integrity Management Department. Today's webinar is titled Understanding Risk-Based Inspection, or RBI for short. We are proud to welcome Mr. Steve Hall with AVH Engineering, who will be presenting today's webinar. Mr. Hall has over 45 years of experience in this industry, and of that, more than 20 years of practical hands-on experience in implementing RBI programs. We are very grateful to have Mr. Hall and AVH Engineering, who have been a valuable strategic partner of Loenbro since 2015. We hope that you'll gain a solid foundational understanding of RBI programs from this training. Please note that all participants are in listen-only mode throughout the duration of the webinar. If you have any questions that come to mind at any point throughout, please feel free to enter them in the chat tab, and we'll try to answer any of those questions at the conclusion of the presentation. Before we get started, we're going to send out a couple of polls just to kind of get an idea of who's attending today. I'll ask Ms. Sabrina if she'll go ahead and submit the first poll, and please submit your answers just as soon as you can. Right, hopefully getting close to all the results. See if we can share those. All right, so a little 50-50 here on experience with RBI. Let's do one more, Sabrina. Obviously, more for those that have experience with RBI. All right. And good to know, so good bit of some, still some none. And just so that we put you to work today, let's do one more just for the sake of things. Okay. All right. So a lot of vendors here. Well, thank you very much for your participation with that. And with no further ado, Mr. Hall, please feel free to go ahead and take it away.
Okay, thank you. I appreciate the introduction. This is a basically high-level understanding risk-based inspection to introduce you all to RBI. Now, RBI is parts of asset integrity management, which includes, operations, IT, regulatory bodies, management, maintenance, and inspection. I'm going to concentrate, focus primarily on RBI and a little bit on IOWs, which stands for inspection operating windows. They can be developed easily after developing or undertaking an RBI assessment. We may have skipped it, but there's another slide in here just before this one. It has all the acronyms that I'll be using. I will usually explain them out, but we'll be issuing this in PDF format to those that would like to have it, so that'll help you there. What is it? RBI is a documented methodology, a thought process that factors risk into inspection and maintenance decision making. It's a hybrid technique which combines the disciplines of risk analysis and mechanical integrity. Typically in the industry, it only covers the breach of pressure containing hardware. Why was it developed? Most pressure equipment contains flaws, and those flaws don't cause problems. Most of them don't, but a few of them do, and can cause catastrophic failure. So the idea was to find and address potential critical flaws and high-risk service cost effectively through a repeatable methodologies. So that was why RBI was developed. And as a matter of fact, if we look at a facility, a lot of times 80% of facility risk is associated with only 20% of the pressure equipment. So this allows us to concentrate on that 20%. What are the typical objectives? Avoidance of catastrophic failure, getting a safer plant. Be able to attain longer intervals between internal inspections while maintaining the same level of risk. Focusing resources and effective use of inspection and maintenance personnel, documenting the methodology for factoring risks into inspection, and it's a proactive application of new techniques and allows for that. That fourth bullet point is very important, primarily when one is going through a sustainment program, or if there's ever any kind of investigation of a fault or something like that. It's documented of how the decisions were made to do, how often to do inspections, and so on. There are three basic questions that are considered when establishing the basis for defining risk. They are: what can go wrong? How often might it happen? A likelihood, and what are the effects? Consequences. A fairly easy understanding is risk is the combination of frequency of some event and the consequence of that generating negative associated with that event. So when we're looking at the risk, when we look at COVID risk, it is what is the frequency of being exposed to that, and what are the consequences of that, or what is the probability of a what's the risk in flying, and it's the probability of the aircraft coming out of the air somehow, and we all know what the consequences are. Typical RBI implementation process. First of all, we have preparation phase, determining our goals and objectives, assembling resources, determining our approach, and determining the scope. The next thing we go into is analysis, or assessment, when we collect the data and determine the consequence of failure, likelihood of failure. That's what COF and LOF stand for, and do the risk ranking. And then finally, we go into an implementation phase, which is basically taking the results from the assessment and developing inspection plans, or developing integrity operating windows, and maybe developing damage control documents, or CCDs. There's also this other here, but primarily that's a matter of if after the risk assessment is found that the risk is too high to meet corporate requirements, then maybe other changes may be required. In other words, some systems may have to be operated differently, or design change may have to be implemented to keep that risk within acceptable levels, because inspection won't take care of it. Finally, the development of inspection plans. If there is no issues, you can go right ahead and implement it. If we find out that there are some items in there that are way too high, or for some, what I will say, quote unquote, off the chart, is to undertake a fitness for service and take remedial action. And then after that, those plans need to be sustained by basically on a regular basis of updating your RBI process through the memorandum of change. Preparation phase. Oops, sorry. Goals and objectives, and this goes through why are we doing it? What knowledge is required? Who will be on the RBI team? What are the roles? Who's responsible and accountable for what? What facilities, assets, and components will be included? What approach, methodology, or software will be used? What data are to be used? When will the assessment be completed? How long will the assessment be in effect, and when will it be updated? How will the results be used? What benefits will be derived from the program? So basically, when you're setting up a program, a lot of these need to be addressed, and some of these will be covered as we go forward. Types of risk analysis, we've got a level 1, which is basic. Now, this is primarily in the oil and gas, chemical environment. Level 1, qualitative risk analysis, simple, brief prioritization of equipment. You maybe easily use a spreadsheet with quantitative questions and rate items, high, low, medium, what have you. This is usually developed by a group of corrosion engineers, process engineers, and inspectors to take a look at that. Level 2 is a semi-quantitative risk analysis. It's more detailed in prioritization and planning. There is a way to rank things within there using people that have had, say, using subject matter experts, so those that have maybe 10 to 15 years experience working at plants and can understand damage mechanisms and contaminants that may be involved in process streams and so on and so forth. And then finally, there's a quantitative risk analysis, basically in-depth analysis. And this is typically that is implemented through software that provides for using the detail of the RP 581 API RPI 581 methodology. Which one do you want to, would we recommend that you use, or do you want to decide to use? We understand, perform the minimum level of analysis necessary to provide information adequate for decision making. If I'm looking at one piece of or two pieces of equipment and a very small type of thing, qualitative will probably more than sufficient to do that. But if you're going to do a detailed analysis, you're going to need software, et cetera, so you can get repeatable results. Okay, detailed analysis, when not necessary, doesn't benefit the decision maker, but may inappropriately use resources which could have been spent reducing the risk. Also want to point out, accuracy and precision are not the same thing. While quantitative assessment can be more precise, in other words, I may find my probability of failure out to the second or third decimal place. I will show you in a minute or two why it doesn't matter. And also, if I'm precisely defining the area that my consequence is going to cover, again, it doesn't mean you need to be more precise. You can be accurate without being precise. Okay, by inappropriate using resources, time and money, you can actually increase the risk because you're taking away resources that could be used, again, to manage the risk once it's done. The approach is basically in a semi-quantitative is we use weighted ranking factors for relative ranking centered on equipment and process-specific conditions. The quality of the data are taken into account. Component data are benchmarked and qualified, and the basis for all decisions is documented. And again, I want to point out that's very important. While the API 581 approaches take into account that, they also use generic industry data as a starting point in terms of probability of failure, and provide another piece of evidence to assist with other pieces of evidence to assist with the risk ranking. As you can see, we tend to favor the semi-quantitative approach. The RBI software consideration. Are you going to have the software be the IM program, or does it support the IM program? We certainly recommend that it support the IM program. There may be things within the software that, not address everything you need to in that. Okay, what are the requirements? Do you want to use, you need to develop your requirements of what you want to do. Quantitative, semi-quantitative, or qualitative? Do you want to include inspection planning and management? Are you going to, is it going to be integrated with other tools such as SAP or other scheduling programs, your CMMS? What are the corporate IT requirements? Sometimes that can be and I'm probably speaking out of school, a pain in the neck. And also, what kind of training are you going to need to obtain? Okay, should you, as an owner user, obtain a license or have the vendor provide? There are cost considerations when it comes to that. We always suggest that the owner user obtain a license because to keep being able to support it after the initial RBI is accomplished, in terms of sustainment. And the other thing we look at that can affect your license cost is try to avoid bells and whistles. There's a lot of RBI software out there that has a lot more than you need. Determine the scope. Okay, am I just going to do the assessment? Do I want to develop the inspection plans? In other words, taking out, using in determining inspection frequency and techniques, which typically software can do based on the risk. Just need to, for each different entity or owner user, that can be configured. Inspection ISO, are you going to develop ISOs? Are you going to assign corrosion monitoring locations? And finally, do you want to do a visual and NDE inspection after the inspection plans are developed and the risk ranking is done to verify where you're at? Okay, also, do I want to develop integrity operating windows, and do I want to develop corrosion control documents for documenting the RBI? What coverage? What type of units am I going to be looking at? Just the process, or are I include the utilities? Fixed equipment, piping circuits, those are normally included. PRDs or pressure relief devices, and or 650 tanks. Okay, preparation and setting up the team process. Here's the who's going to be on there: project manager, data clerks, reliability, operations engineers, metallurgical corrosion engineers. Let's see, somebody. Oh yeah, we got the process engineer. I tend to forget to bring them in. A lot of the RBI is driven by metallurgists and corrosion engineers, just as an aside. Okay, cost. It's typically priced per equipment item, and then we have a metric where we can determine the number of circuits based on the number of vessels or fixed equipment items we're going to be looking at. Okay, what is the software going to cost? Okay, time. How long is it going to take to get it done? And again, this is very size dependent and dependent on the availability to gather and enter in required mechanical process and other data. Okay, one thing I forgot is I believe, Sabrina, you had a poll to find out the who's using what software. Can you go ahead and run that? Thank you, appreciate it. And thank you out there for doing that. And then what kind of software? Okay, interesting results. Okay, and the data sources, on this one, we want to run one more poll and find out, are you responsible for managing the data at your company? Thank you, appreciate it. Okay. Okay. Typical data sources are original design data. This we need for the mechanical information. We want to know how big it is and what it's been through. Has it been post-weld heat treated? It might be. Basically, we're going to need to know the material spec and what have you. So we'd like to get design calc. We can get it a lot of times from design calcs. The easiest one is a U1, but they're not always available. User specifications from design, fabrication drawings, material reports, and original hydro test UT measurements if they were ever done. The idea is to look at all of these to try to get the information we can get instead of saying, oh, I don't have it, I can't do it. On the process data side, we need PFDs and PNIDs, process flow diagrams, piping instrument diagrams, so that we can figure out, what's going to be affecting what. Material balance information, if the software is sophisticated enough to take into account, if I have a mixture of flammable, different flammable rated stuff, plus some hazardous material as well from a toxic standpoint, this is usually more applicable to chemical plants. We can also get a lot of good information from SDS sheets or I've forgotten it. You can look at the safety data sheets. Okay, and then of course, maintenance and inspection and operational history are all very important that allow us to get information to do what needs to be done. Okay, the assessment process. Okay, first of all, we review the documents that we have picked up to pull out the information. And typically we'll take that data and have it entered into software templates to populate the RBI software. We do it we start with the COF process, consequence of failure process, followed by the likelihood of failure process. And in the consequence of failure process, which we are doing using software, typically, we go through and determine various and sundry things affecting the process, looking at the process material, temperatures, pressures, and then trying to determine the release and what type, calculate an initial rating, which is usually algorithms buried within the software to see how bad my consequence may be. API 581 measures it in an area and or dollars lost if you want to. And then the next thing to do is to identify those things that can modify the consequence value, either up or down. It may aggravate it, it may mitigate it, and then come up with a final COF. Right after that, we'll review the facility, usually have subject matter expert who's got a wide range of experience. We have one guy that's got almost 40 years of experience doing this. He can look at the material of construction and the process fluids and make a decision on what damage mechanism. In fact, he can probably do that in about 5, maybe max of 10 minutes. He's got that kind of encyclopedic knowledge. Anyway, digressed. Okay, you'll ID the damage mechs and the failure modes, and again, look at aggravating and mitigating factors, review and adjust the LOF, and then we come up with a risk rank. COF data that we get, process chemical safety data sheets, as I was saying. There's one software that we're aware of, uses the National Fire Protection Association ratings, which if you've ever been out and you see on trucks a lot of times, or on oxygen tanks or something like that, you'll see a diamond with 4 different characteristics in there, one being flammability, toxicity, reactivity, what have you. Okay, what is the density or the inventories that are going to be released? You know, how much mass? What's the state? Is it gas? Or is it liquid? Confidence in the analysis. Taking into account, has there been feedstock changes? This is probably it's the oil and gas side of the business, especially if one's was using sweet and they switch to sour, or vice versa. Okay, let's look at the leak rate, which is tied to damage mechanisms. Which means there's some damage mechanisms that will result in a total break, and there's others that will lead to a pinhole leak. Okay, what are the operating conditions? Temperature, pressure. How many people, equipment, or buildings are in the area that could be impacted? What is the environmental impact? You know, the presence of streams, lakes, etc., nearby, that sort of thing. Has a HAZOP study been done? Results from that can also be input into that. And then, is there mitigation equipment available, like a deluge system? You know, how quickly can I isolate it, et cetera, et cetera. The kind of the thought process, and this is more implicit than it is explicit, what we do is you look at, you know, the idea is the pressure boundaries is breached, and I can get 2 outcomes that I can arrest the leak and it's no longer a problem because I shut it down and we had no leak, and so on and so forth. Okay, if it's not arrested or mitigated, it can continue. However, if it disperses, there's no consequence. On the other side, if it does, then you find ignition source or receptor, and destruction occurs. So that's kind of the logical thought process going on, and which is usually embedded in the software. Now, likelihood of failure analysis. We define the damage potential. Look at the materials of construction history, and again, what are the process streams and containment composition? Once that's done, and we're not only looking at internal corrosion, we're also our damage mechanisms, also external damage mechanisms as well. We identify the failure mechanisms, determine the potential failure modes for the damage mechanisms, and assign a damage rank based on the possibility of occurrence and the failure mode if it's not detected. Okay, we look at and try to define the damage potential. And this is a kind of a repeat of the previous slides, but, you know, again, we're looking at the MOSA. How old is it? What kind of a history and inspection data do I have on that? Is the inspection data showing an increasing trend, maybe in increasing corrosion rate or a higher potential for a cracking mechanism? What is the process stream's contaminants, composition? If I've got a sour stream, that's really going to impact my potential corrosion rates. Okay, identify again potential damage mechanisms. Now we typically will use those listed in API 571 or API 581, but that doesn't mean we cannot use, or you cannot use, those that you have identified yourself. Okay, so we basically look at corrosion rates, and if it's really tough, may suggest getting the results of a remaining useful life assessment, but I wouldn't do that unless it's the cost of it is worth the return. Okay, and then we decide the damage rank based on possibility of occurrence and the failure mode. Okay, excuse me. Considerations when you're looking at the likelihood of failure. What type of corrosion control is underway? Is there any cathodic protection? What inhibitors are being used? Is the vessel or the lines clad or lined? What are the process considerations? And I mentioned one before, had we had a process change, what have you. Okay, yeah, the feedstock change, confidence in the stream analysis, transient and off normal operations. So we need to find out if the thing has been run hot or hard for various and sundry reasons. Okay, what's been the scope, frequency, and techniques used previously? Of course, if this is a green field, we don't really have to worry about that. And what is the quality of documentation and plant experience? We have had software that could sit there and address that and decrease or increase the POF, the likelihood of failure number. Okay, other failure factors: incorrect design from the get-go, incorrect material. Somebody used carbon steel when they should have used stainless steel, and this may have happened after the plant was built, and somebody's, oh, here's a pup piece, I'll just put that sucker in there. And this has happened before, and people have gotten in trouble because maybe a plant couldn't operate for 6 months because of an explosion or fire. Okay, construction defects, layup, welds, and sometimes if they haven't been flushed correctly during startup, you can get junk taking care of that. And then hydro testing contaminants. Okay, when we're looking at risk and measurement of risk, we're looking at the consequence of failure is usually set up as a business consequence, like low, medium, or high, or damage consequence. The two differences here is this is usually bucks, damage consequence. Safety, health consequences. Now the damage consequence is more from what else has been ruined or affected. I was at one company where we did a post-fire damage assessment and had to go through and do some fitness for service assessments before they could start up again. Okay, what are the safety health consequences and what are the environmental consequences? Now, and again, like I was saying, they're usually determined in terms of low, medium, high, or in terms of an area such as API 581 or dollar values. The likelihood of failure is usually measured either in frequency per year, low, medium, high, or the likelihood of failure. A lot of times we'll be taking the frequency and converting it to a likelihood of failure. This is when we've done through all this, we end up getting our answers, basically, whether it's semi-quant or quantitative, of putting it into a matrix. In other words, we determine if I have a low probability of failure and the consequences is nothing. In other words, I get a leak every 20 years, and what leaks is, water condensate or something like that. It's of no problem. But then we can go up to a very high risk where something is set up such that it can have a high consequence, a big explosion or a large toxic cloud, and a high probability of failure. And typically, and we're going to be taking these results, what we want to do is to take and move this down to here, from the top right-hand corner down to the left hand bottom place. We want to try to get the risk down in either the yellow or green areas, or these can also don't have to be 5 by 5. They can be set up to suit whatever the requirements of the owner user wishes for their corporate risk assessment. And it could be 8x8, or one software that we have dealt with has a 4x4 matrix. But the idea is programmatically trying to, identify and get the risk of these items. This is relative risk for the plant. This is not absolute risk. And we don't need the absolute risk for this. So the interesting thing is API 581 approach takes, and it will calculate the probability of failure based typically on generic data down to quite a few decimal places. And also if one uses their second level consequence approach, where you have to, measure what the, let's say a cloud distance or the probability of ignition, all these other things, is they still come up with these numbers, and they may be out to second, third decimal place. They still go back and put them into a matrix just like this that are delimited by, the values. Okay, we've gone through, we've developed our risk ranking. What am I going to do with this? It's like doing RCM. Hey, we did an RCM. Well, what did you do with it? Well, in this case, as I'd mentioned, one of the key things coming out here is inspection planning. Identify the risk sensitive, you prioritize the equipment, identify likely damage mechanisms and the frequency. And since we have that risk matrix, we can assign based on the COF and LOF maybe a recommended frequency. If it's really low, then basically I can have a quite extended time between inspections. If it's less, then we do that. But now once I've got that, then I can basically output for each piece of equipment circuit how often I'm going to inspect these. And within the software, you can set up to have it align with at least for internal inspection, have it aligned with your turnarounds. Okay. The other thing is, because we're going through and identifying the damage mechanisms, we can associate different inspection techniques with the damage mechanism, such as the damage, the inspections that are recommended can meet the needs or have the highest likelihood of detecting potential degradation. Okay, and from that you can get a specific plan for each item. We have also been involved in isometric drawings, ISOs for vessels showing, where CML should be placed for nozzles and heads and what have you, through the location of likely damage. And then finally, determine whether you want to do a baseline visual or non-destructive inspection after the RBI has been completed and the inspection plans developed. Okay, one of the other outputs we were looking at, and we have found that this can be quite useful, is to develop a corrosion control document. And it basically supplies information coming in from a lot of different areas where, if it wasn't done, the inspector or whoever has to go to a number of different documents. What this does is, because we're looking at all the different information sources, is that you get a system flow narrative, you get the controls, you get an idea of what the system information, which vessels are included, which circuits are included, and what was the damage mix assigned. Recap the system parameters, chemistry, contaminants, a listing of the primary damage mix, a discussion of the appropriateness of material selections, and appropriate inspection techniques for identify damage mechanisms. A lot of this is covered in API 584, I believe, but there's usually, in general, it's been laid out, as opposed to providing, what kind of format, exactly what should I include. Finally, IOWs. What is an integrity operating window? It defines the maximum and minimum operating process variables that should be maintained in order to meet the intended design of the life. In other words, I want to run inside a pressure, temperature, flow rate type of regime that'll keep me within the green. And those may have, values on the sensors that shouldn't be overrode. Now the next thing is, we know that sometimes they do get overridden, and you'll get into what we call the yellow zone, which is you're still within a safe operating limit, but when you get up to the red, you're even going beyond the design envelope. And the idea is to take and either get information from sensors and or from I'm trying to think of it, walkarounds, on a weekly or daily basis, to gain that information. Okay, and so the reason it's needed is what we're doing when we do RBIs, we're taking a snapshot. What IOWs allow you to do is to get a running idea of the, at least that you're running within the parameters that don't cause a damage mechanism to start or to exacerbate one that's already there. And you're getting sometimes real-time information on that. Okay, and when we say real time, in essence, what one will do is to take information from the sensors that leads down to the DCS, and depending on the criticality of it, it can either alarm and or just pass through that down to the DCS. I mean, careful study has to be made of what it is, and then you have a means for on an exception basis for an integrity engineer to go in and say, wait a minute, this happened, we need to change something and go from there, because this is potentially what this could have done. We've also found it's a good way to provide information. We find it also, it's a good way to means of communicating between ops, engineering, and maintenance based on a common set of concepts and definition, and ending the problem of operation say you didn't fix it right, and inspection saying you need to quit running that stuff the wrong way, type of thing, so that there's an understanding on both sides. Okay, it's an established process for recognizing and mitigating the effects of operating plant equipment. Okay, they facilitated, which I was talking about before, they facilitate automated data analysis, eliminating the need to manually review an asset's past operating history. And they can provide real-time notifications of any of the predefined boundaries approaching dangerous territory, again, by alarming that maybe on the out of the DCS. Where can these be, RBI, IOWs be applied? Or if you're looking at infrastructure, it's at process plants, including upgraders, oil processing, refineries, chemical plants. We've done it on pipelines, at power plants, typically on fired, fired heaters, boilers, and even done it on offshore platforms. And what's included? Pressure vessels, piping, tanks, pressure relief devices. Okay, the benefits. Okay, there's 2 pages here of what I would call non-dollar benefits. Regulatory compliance. This is how RBI got started back in the early 1990s. OSHA came out and said thou shalt do thus and so. Okay, improve safety, reduce risk. There are long-term cost benefits, and I'll show you an example here in a minute. It focuses the inspection. More than likely, it'll reduce your CMLs. Extending intervals can be used to extend intervals beyond the API 510, 570, 693, and 576 boundaries. The opportunity to reduce internal inspections, not only by extending the interval between inspections, but also by smartly looking and see if the rules that surround doing online inspection in lieu of internal can be done. They can help with turnaround planning by reducing the number of items that may have to be inspected internally on a turnaround basis. The use of new inspection NDE technology and informed, documented, and defensible decisions. Again, I can't emphasize that documentation. Okay, you can avoid catastrophic failure. Okay, when you're looking at the turnaround impacts, the turnaround interval can be increased. This is if it's not being driven by some other reason, i.e. a catalyst change or what have you. And if it's the turnarounds have been driven by issues with fixed equipment. Okay, potentially turnaround durations can be decreased because I just don't have to look at as much equipment. Okay, unexpected damage findings may be reduced, especially if one takes into account IOW information. Okay, and again, a turnaround inspection cost reduction. Okay, decreased unplanned outages due to pressure equipment or piping circuit failures, and reduction in cost due to excessive inspections of low risk items. Now, these cost savings, they're real. And at one time or another, each one of us in our various and sundry professional lives have seen this. To see this chemical plant, the 2-year turnaround cycle from 4 to 6 years, saving of $11 million every 2 years. Now, this was in the state of Tennessee, which had a mandated "thou shalt do it" every 2 years, and they were able to convince the regulating authority that doing an RBI, they were not increasing any risk. Okay, doing an API evaluation of gas plant. Okay, turnaround time shortened by 10 days. $10 million every turnaround cycle. Ethylene oxide unit. Okay, 80% vessels are now inspected at greater than 10 years, rather than having to do everything on 5. Ethylene unit. Okay. Results of study resulted in $1 million, greater than $1 million on a turnaround. Okay, and then this alcohol unit, study of 500 turnaround vessels and 500 PRDs, resulting in greater than 500,000 savings on the first turnaround right after the RBI. So, as there used to be a senator from Illinois by the name of Everett Dirksen, his favorite saying was $1 billion here, $1 billion there. Pretty soon it adds up to real money. So we can see that this does it. Now, this is an example of a return on investing in doing an RBI is based on looking at a North American refinery. As you can see, the implementation cost was around $435,000. We looked at 500 items of fixed equipment, 2,000 circuits. And what we did when we got done is based on the equipment counts and looking at the average inspection count, we were able to compare the cost savings that would come if I did worked a full RBI strategy over 20 years. I would get rather than doing everything every 5 years, I'd get a $35 million savings, and that went up to, if I included the piping in there, it went up to 42 million. And if I grouped circuits, I don't know if everybody here is familiar with that process of finding like circuits and with the same characteristics, same risk, et cetera, and using one, inspecting one, and then if I find out that there's issues with that one, then I will go look at the others. So that went up another 7 mil. So as I said, pretty soon it adds up to real money. So look at what you're spending on, and you look at what the reduction in availability or productivity is impacting your plant, and one can probably come up with a good cost benefit reason for going ahead and doing that ARBI. And that is it. In essence, the last slide was supposed to show how to get either Sabrina or myself, or
All right. While you're scrolling to that, Mr.
yeah.
Steve, we definitely appreciate it. No questions came through the chat, but we know that doesn't always mean there aren't any questions that exist. So the contact information is on the screen. You know, a lot of times, especially if questions are more detailed and involved, you want to know how you might can make this work for you, or any other questions related to RBI. Feel free to reach out to any of the contacts posted here. So with that said, I want to say a big thank you to Mr. Hall for your time and effort in putting all this together and presenting this very good presentation. I'd also like to give a big thanks for everybody that was able to attend today. We all hope that you gained a good understanding of RBI programs, the implementations, the benefits, and everything in between. If you'd like a copy of this presentation, or like I said before, any other information, feel free to shoot an email to any of the contacts there, and we'll be happy to provide answers to questions or a PDF copy of this for your use, viewing pleasure. But anyway, thank you again, and we hope all of you have a great remainder of your day.